Hi, I'm Dr. Incognito. In this video, we're going to solve a linear system. I have on the board here a 4x4 linear system. I have 4 equations in 4 variables, x, y, z, and w. And each of the equations is linear because the variables appear with a coefficient and to the first power. So 4 linear equations in 4 variables. I would like to solve the system, which means I would like to find values for x, y, z, and w which satisfy all 4 equations simultaneously. So the method I'm going to use to solve this system is to create the augmented matrix for the system and then reduce the coefficient matrix to row echelon form using Gauss-Jordan reduction. So the coefficient matrix is 1, 1, 1, 1, 1, negative 1, 1, negative 1, 2, 1, negative 2, 1, 4, 1, 0, 1. And then I'm going to make the augmented matrix. I'm going to put the constant terms on the other side of this divider. 1, 2, 3, 6. So that's just a shorthand way of writing this system. Now what we're going to do is use elementary row operations to carry the coefficient matrix, which is this 4x4 matrix on the left side of the divider. We're going to carry this coefficient matrix to row echelon form. In the upper left-hand corner, I would like to start with a 1. And there's already a 1 there, so I'm all set. And this 1 I'm going to use as what's called a pivot. I'm going to use that 1 to make the numbers below it all zeros. So the first operation that I'm going to do, I'm going to do row 2 minus row 1. So row 2 minus row 1. And while we're at it, we're going to do row 3 minus 2 times row 1, because 2 minus 2 is 0. So I'm going to do row 3 minus 2 times row 1. And then to use that 1 to make this 4 0, I want 4 minus 4. So that's going to be 4 minus 4 times row 1. So row 3 minus 4 times row, sorry, that's row 4. That's row 4. Row 4 minus 4 times row 1. So I'm going to do these 3 operations. Row 1 will stay the same. Now let's look at what happens to row 2. I'm doing row 2 minus row 1. So I'm going to do 1 minus 1, negative 1 minus 1, 1 minus 1, negative 1 minus 1, and 2 minus 1. So 1 minus 1 is 0, negative 1 minus 1 is negative 2, 1 minus 1 is 0, negative 1 minus 1 is negative 2, and finally 2 minus 1 is 1. And now let's zero out that 2 by doing row 3 minus 2 row 1. So 2 minus 2 of those, 1 minus 2 of those, negative 2 minus 2 of those, etc. So 2 minus 2, 0. 1 minus 2, negative 1. Negative 2 minus 2, negative 4. 1 minus 2, negative 1. 3 minus 2, 1. And then row 4 minus 4 times row 1. 4 minus 4, 0. 1 minus 4, negative 3. 0 minus 4, negative 4. 1 minus 4, negative 3. And 6 minus 4 is 2. So now this pivot had just been used to create zeros below it, effectively eliminating the variable x from equations 2, 3, and 4. So I'd like to continue the process by eliminating the variable y from some equations. So I'd like this one right here, I'd like to use that as a pivot. that entry. However, I want that to be a 1. I have a couple of choices. I could divide this row by -2, but that would lead to a fraction over here. So since there's already a -1 here, let's switch these two rows, and simultaneously I will divide or multiply this row by -1. So I'm going to first I'll multiply row 3 by -1. So -1 times row 3. And then after I multiply that by -1, 1, 4, 1, -1, I will switch row 2 and row 3. So I'll do a row swap. So the top row is going to stay the same. Row 2 the new row 2 is going to be the negative of this one. So 0, 1, 4, 1, -1. Row 3 is going to be the old row 2 because of the swap. -2, 0, -2, 1, and row 4 stays the same. 0, -3, -4, -3, 2. So now I have a leading one that I can use as a pivot in the second row, second column. And I'm going to use that pivot to make the numbers below it zeros, eliminating the variable y from the third and fourth equations. So I'm going to do row 3 plus 2 times row 2, and I'm going to do row 4 plus 3 times row 2, because -2 plus 2 is 0, and -3 plus 3 is 0. So I have to do -2 plus 2 of those, row 3 plus 2, row 2. And I have to do here -3 plus 3 of those, so -3 plus 3, row 2. And we get, the first row will stay the same, the second row will stay the same, third row, 0 plus 2 zeros is 0, -2 plus 2 ones is 0, 0 plus 2 fours is 8, -2 plus 2 ones is 0, and 1 plus 2 negative ones is -1. That was 1 plus -2. That's -1. And in row 4, 0 plus 3 zeros is 0. -3 plus 3 times 1, -3 plus 3 is 0. Then -4 plus 3 fours, -4 plus 12 is 8. Then -3 plus 3 ones, -3 plus 3 is 0. And finally, 2 plus 3 times -1. So 2 plus -3, 2 minus 3 is -1. And continuing this process, I would like that number to become a 1. But before I just blindly divide by 8, let's notice that these two rows are exactly the same. So what I'll do, I'll take advantage of that by just saying, let's do row 4 minus row 3, so that these become zeros. So 1, 1, 1, 1, 1, 0, 1, 4, 1, -1, 0, 0, 8, 0, -1, 0, 0, 0, 0, 0. So here we have a row of all zeros. If the coefficients were 0, but the constant term were not 0, which it is in this example, but if that were not 0, all 0 coefficients with a non-zero constant term, then the system would be inconsistent and it would have no solution. But that's not the case here, so we keep going. Let's also do 1/8 times row 3. 1/8 times row 3. So instead of writing this all over again, let me make that into a 1 and that into a -1/8. So 1 and -1/8. And what we have now is called the row echelon form of the 4x4 coefficient matrix. The first non-zero entry in each row is a 1. Below those leading ones are zeros, and the leading ones go to the right as you go down. And all 0 rows, if there are any, and there is one here, are at the bottom of the matrix. So these conditions make what's called row echelon form. Row echelon form. And they transform our system of equations into a much simpler system. They transform our system of equations into, well, the first equation actually never changed. X plus y plus z plus w equals 1. The second equation is y plus 4z plus w equals negative 1. The third equation is z equals negative 1/8. And the fourth equation is 0 equals 0. So doing the operations, the Gauss-Jordan reduction, our matrix tells us that our original system is equivalent to this system. So what are the solutions of this system? First, notice that there are three leading ones in this row echelon form here. There's a leading one here, here, and here, corresponding to the variables x, y, and z. There is no leading one corresponding to the variable w. And so when writing our solutions, what that means is that w is what's called a free variable. So the value for w could be anything. You could choose anything at all that you like for the value w and get a solution to the system. So we'll start by saying w could be t, which could be anything. We'll call that a parameter, and t is any real number between minus infinity and infinity. T can be anything. What about the other variables? The third equation here, z equals minus 1/8. Well, that simply tells us that z has to equal minus 1/8. No choice there. And then the previous equation, y plus 4z plus w equals negative 1, since we already have w equals t and z equals minus 1/8, we can plug those in. So first, y equals negative 1 minus 4z minus w, and that's negative 1 minus 4 times negative 1/8 minus t. So y can be written in terms of z and w, where w was t and z was minus 1/8. So this simplifies to negative 1 plus 1/2 minus t, which is negative 1/2 plus t. So that's y. There's z, there's w, and finally we can do the same for x that we just did for y. So x plus y plus z plus w is equal to 1. So if I move the y, z, and the w to the other side, I get x equals 1 minus y minus z minus w. And we have expressions for y, z, and w already, so plug those in. We are doing what's called back substituting. So 1 minus y is negative 1/2 plus t minus z, which was negative 1/8, minus w, which is t. So there's x. And we can simplify this. It's 1 plus 1/2 minus t plus 1/8 minus t. I think I made a small error here. This should be a minus t, and I wrote a plus t. That's negative 1/2 minus t. And I just used that here. That should have been negative 1/2 minus t. And then distributing that minus, that makes that a plus. And so t minus t cancels. And we're just left with 1 plus 1/2 plus 1/8. And that's 8/8 plus 4/8, that's 12/8, plus 1 more is 13/8. So x should be 13/8. So altogether we can write the solutions x, y, z, w have the form 13/8, negative 1 minus negative 1/2 minus t, negative 1/8, and t, where t is any real number. So there are infinitely many solutions here, because you can choose t to be anything you like, and that will affect y and w, but x will always be 13/8, and z will always be minus 1/8. Okay, so that's the solution to our linear system. We wrote down an augmented matrix, and we used Gauss-Jordan reduction to make a row echelon form, and then once we had a row echelon form, we could figure out the solutions pretty easily. Okay, thank you for watching.